Hello friends, in the last two episodes we discussed about X-ray diffraction technique. We discussed about the varied applications offered by the XRD or the X-ray diffraction in the study of a periodic structure from a crystal. But if you remember, we had in one of the earlier lectures we have listed out three different techniques useful for the study of crystal structure. So, among them other than XRD, the techniques were neutron diffraction and electron diffraction. In this episode, we will discuss in brief about those two techniques. So, let us start with neutron diffraction. In our discussion of the XRD, we told that X-rays scatter from electrons in an atom. But when it comes to neutron diffraction, the neutrons, which are the incident particles instead of the X-rays in an XRD, are uncharged, and they can scatter almost exclusively from the nuclei rather than from the electrons, and that interaction or the scattering is based on the nuclear forces. So, this technique was very significant technique that in 1994 the Nobel Prize was awarded for the discovery of neutron scattering studies. So, it was basically awarded to two scientists. One is Schul, where he found out the application of the neutron scattering to study the antiferromagnetism, and the second person was Brockhaus for his innovations in the field of inelastic scattering based on the neutron. So, you all know that the Nobel Prize is awarded on those kind of fields where there is a significant application of the technique which is very much valuable for the humanity. So, why Nobel Prize, or more specifically what is the relevance of neutron diffraction, so that it needs a worldwide attention. The X-rays scatter very strongly from the heavy atoms and weakly from the light atoms. This point we had discussed in our earlier episode, because it is dependent on the electronic density, and the lower atomic number atoms will have lower density of atoms, and therefore X-ray intensity or the X-ray diffraction intensity will be lower from the lower atomic number elements. So, this makes it very difficult to see light atoms like hydrogen in a solid. Further, it is hard to distinguish atoms that are very close to each other in their atomic number because of their dependence on the electron number, and therefore, because of the similar number they almost scatter the same amount. In comparison, for neutron scattering, the nuclear scattering length varies rather erratically with atomic number. Erratically means that the intensity offered by the neutron scattering is not really dependent on the atomic number. Further, one can usually distinguish atoms with similar atomic numbers rather easily, which means that even you would be isotopes, all those kind of stuffs you would be able to identify based on the neutron diffraction. Another relevance is with respect to the spin which the neutron possesses. The neutrons do possess a spin. So, what is the advantage of this? Either they have up spin or they will have down spin. So, because of the spin, they can distinguish between electrons in the unit cell having spins pointing up or down, because this interaction energy which will be offered by the interaction between the neutrons and the electrons is depending on their relative spin orientations. The scattering of the neutron from the electrons is much weaker than the scattering from the nucleus, but it will be still observable. This factor makes it very useful in the studies of magnetic domain structure or spin arrangement. So, one of the wide ranging or most widely used application of neutron scattering is in the on the studies of magnetic materials, and newer and due to because of that reason we are seeing more and more facilities developing for the study of magnetic structures based on neutron diffraction techniques. The scattering mechanism for the neutrons in the is the interaction between the neutron and the atomic nucleus present in the crystal. This interaction is referred to as strong interaction. As I told you, it is the nuclear forces. It is the reaction responsible for holding the nucleons, the nuclear forces, the neutrons and the protons stored in the nucleus. Being electrically neutral, the neutron does not interact with electrons in the crystal, whereas the spin of the neutrons will start interacting with the electrons. Thus, unlike the X-rays which is scattered entirely by the electron, the neutron is scattered entirely by the nuclei. This helps in a deeper penetration of the neutrons. At this point of time, I should tell you that based on our history in XRD, the rules which with which we studied for the or analyzed the XRD, which is basically Bragg's law, is valid in the case of neutron diffraction also. So, what is the kind of neutrons which you use, or what is the kind of source of neutrons which you will be using? So, what is the criterion for choosing? The criterion for choosing should be, we should be able to study the crystalline structure. As we already discussed upon that, the period and the distance between the planes or the lattice parameter of a crystal is typically of the order of angstroms, which means that the radiation which is used for study of the periodicity of the crystal structure should also be of similar order. So, the formula if the formulation for this would be can be taken from the help of the de Broglie relation, lambda is equal to h by p, right. So, if you express the p in terms of energy, so what is the relation? E is equal to p squared by 2m, right. So, if you substitute this E is equal to p squared by 2m into the relation of lambda is equal to h by p, you will reach into an expression of lambda equal to 0.28 divided by e raised to half, assuming that E is in electron volts, E is expressed in electron volts. So, 0.28 divided by e raised to half will give you the lambda. So, if we substitute absolute the lambda to be of the order of angstroms, you will get the energy to be something similar to the what is offered by the kT. K is the Boltzmann constant and T is the temperature, which you must have studied in your classes, which is as a thermal energy we call it. So, the lambda which is evaluated based on the requirement of the distance between the planes, if we put it in the order of angstroms, it will be coming of the neutrons should have an energy of the order of thermal energy kT. So, therefore, those neutrons which are having a similar energy to that of thermal energy kT are generally termed as thermal neutrons. So, to those people who is not really used to that term, the thermal neutrons, let me briefly put it like this. So, in a typical nuclear reactor, you will have different kinds of particles coming out depending on the kind of nuclear reaction which happens over there. So, but in any case, the neutrons which are produced are generally fast neutrons, basically products of some kind of a fission fission reaction. So, fission reaction producing fast neutrons, right. But we need the neutrons of some specific energy which we sorted out as thermal neutrons. So, this needs to be moderated. So, these fast neutrons are moderated with appropriate targets, and we make them into the energy which is of the order of thermal energy, and we name them as thermal neutrons. There are different applications of thermal neutrons, but for our purpose we can guide these thermal neutrons to appropriate crystal and make a crystalline study of the crystal diffraction study on the crystal of our interest. The thermal neutrons are having an energy of about 0.025 electron volts, are even to the extent that they cannot even interact or disturb even the most delicate materials like the biological materials. So, what is the advantage with that? The advantage would be that you will be able to perform the crystal diffraction study even on biological materials with the help of a neutron diffraction without destroying the sample, which means that you can recover the sample back after your experiment, which is the beauty of the neutron diffraction experiment. Again, one more advantage of the neutron study is that the neutrons have a large cross section for atoms like hydrogen, carbon, etc. So, now I use the term cross section. What is the name of cross section means by? In nuclear physics, a nuclear cross section of a nucleus is used to characterize the probabilities that a nuclear reaction will occur, which means that the concept of nuclear reaction can be quantified physically in terms of characteristic area, as they call it, where a larger area means a larger probability of interaction. So, the large cross section of neutron diffraction towards atoms like hydrogen and carbon etc., makes it again suitable for exploring internal structure of polymers and biological crystals. If you remember, in our discussion on the XRD technique, we told that the XRD technique may not be valuable for studying the low atomic number elements, right? And especially when you want to study very important for technically very important topics like that of polymers and biological crystals, the XRDs fall behind the neutron diffraction, because of the concept of nuclear cross section is not dependent on the atomic number. So, neutron diffraction definitely is having a huge place on getting the information of biological and polymeric samples. Now, coming to the cross section, as we can see in the figure, the neutrons hold a clear advantage in many atoms. So, it is not at all depending on the atomic number. In the figure again, you will see that for a research on appropriate battery material, which is very significant field of research these days, one of the typical battery material could be, say, lithium manganate LiMn2O4. The neutron diffraction is very important. I have put in the image there a comparison between the output from an X-ray and from a X-ray diffraction and from a neutron diffraction. There you will see that X-ray diffraction clearly falls behind the neutron diffraction in estimating the periodicity or the presence of something very important like lithium in a battery material like lithium manganate. So, for such kind of studies, neutron diffraction is unavoidable. But that does not mean that the X-ray diffraction technique becomes invalid. Definitely X-ray diffraction is the technique to start with, but if needed we need to graduate ourselves into the techniques like neutron diffraction. A further consequence of the low energy thermal neutrons is that in inelastic scattering events, neutrons exchange energy with the sample, creating or destroying excitations, which is very that is why the inelastic radiations are termed inelastic, right. So, in the study of these disturbances provides a unique proof for interatomic forces in the materials. But there we should take a contrast with the XRD. Imagine you are taking a X-ray with say wavelength of 0.1 angstrom, which is 0.1 nanometer wavelength, and that if you calculate the energy will come out to be something like 12 kilo electron volt energy, and that is capable of creating multiple ionization of the even the most robust chemical structures. So, definitely neutron diffraction plays a major role in the study of magnetic compounds, the polymeric samples and a whole lot of other samples. Now, let us look into electron diffraction. A beam of electrons incident on a crystal suffers Bragg diffraction in a manner similar to the X-ray and neutron diffraction. So, electron diffraction is again offers something similar to what the other two techniques did offer. So, the electrons like the neutron possesses wave properties, which is very clear to all of us, and the wavelength is also given by lambda is equal to h by p. So, if you write the momentum p in terms of the energy and later in terms of the accelerating potential v, you will get the energy is equal to E into V, where E is the charge of the electron, 1.6 into 10 raised to minus 19, as you know will know. So, E is equal to E into V, and we substitute that expression into the expression for from de Broglie, lambda is equal to h by p, and then you will get the lambda expression in terms of the accelerating potential of the electrons, right. So, that will come out to be lambda is equal to 150 by root V, root of 150 by V. That is for a wavelength of 1 angstrom, which is why 1 angstrom, because that is the order of order in which the periodic structure exists in a crystal. If we substitute the lambda to be 1 angstrom, the voltage will come out to be 150 volt, or the energy of the radiation or the energy of the electron radiation will come out to be 150 electron volt. The mechanism responsible for the electron scattering in the electric field is the electric field associated with the atoms in the solid. The field is produced both by the nucleus and by the orbital electrons in each atom. It is large at the nucleus, but decreases rapidly away from the nucleus. In the latter region, the nucleus is screened by the orbital electrons. Calculations show that the scattering length associated with the scattering of the electrons from an atom is large. What does that mean by? This means that the electron beam is strongly scattered and hence has a short stopping distance, right. The distance is only about 50 angstroms for a voltage of say 50 kilovolts. So, 50 angstroms. So, how you can imagine yourself how much is 50 angstroms or 5 nanometers, right. So, even though the electron beam is restricted to rather a small depth near the surface, which is must be calculated 5 nanometer. So, a 1 micron sample for a typical 1 micron thickness sample, the 5 nanometer is really negligible depth, but that also has some relevance, which is what the electron diffraction is exploring. The depth does nonetheless include a number of atomic layers, so that a crystal diffraction pattern is obtained. It also follows that the electron diffraction pattern is particularly sensitive to the physical properties of the surface, which explains its wide use in the study of surfaces. For example, oxide layers, which is one of the most wide-ranging, having wide-ranging applications, starting from the semiconductor industry to photocatalysis, water purification, a whole lot of techniques. The oxide layers, the study of the oxide layers and its crystallinity can be very well be explored with the help of electron diffraction. For example, in the case of multilayers, which is a very wide emerging field of research these days, electron diffraction would be a good technique to explore. Experiments are actually performed in a transmission usually performed in a transmission electron microscope or a scanning electron microscope as electron backscatter diffraction. In these instruments, electrons are accelerated by an electrostatic potential in order to gain the desired energy and determine their wavelength before they interact with the sample to be studied. The wavelength of the electrons in a 10 kilovolt SEM is 0.12 angstrom, while in a 200 kilovolt TEM the wavelength is 0.025 angstroms. So, what is the comparison there? So, if we compare with the XRD, we were talking about the wavelength of X-rays usually used in the used to be of the order of 1 angstroms, right. Electron diffraction of solids is usually performed in the TEM, and there what happens is that the electrons pass through a thin film of the material to be studied. The resulting diffraction pattern is then observed on a fluorescent screen, which is recorded on a photographic film. Or on imaging plates or using a CCD camera. A typical image you can see in the image which is shown there, so which is an SAED image as we call it. As mentioned above, the wavelength of electron accelerator in a TEM is much smaller than that of the radiation usually used for X-ray diffraction experiments. This allows the diffraction experiment to reveal more of the two-dimensional distribution of reciprocal lattice points. How? I would suggest you to read some books of solid state physics books dealing with evolved spheres to understand. So, you can just search what does the evolved spheres means by, and that kind of a study would tell you how a two-dimensional distribution of reciprocal lattice can be made based on the transmission electron microscope, and which is a very useful technique to start with. So, two-dimensional distribution of reciprocal lattice points. So, it is really a beautiful picture which it would be offered, which means that we would be able to study the lattice distribution on a 2D surface, unlike the case of a 3D surface. As you can see in the figure there, a transmission electron microscope will have sample which is very thin, which will allow basically the electron radiation, which is after all the optics involved in between, will transmit through the signal and then will get focused on a screen down there. But remember that in a scanning electron microscope, the technique is different. It is actually getting reflected out of the surface, and you produce a surface image. You are actually taking a photo of the surface in a SEM. Whereas in a transmission electron microscope, electrons really transmit through the sample, and it is focused onto a plane, and then you make out the real physical picture, or SAED image as the one which I showed earlier. Now, this is the beauty of science also. It is a matter of historical interest. In 1927, it was Davison and Germer observed the scattering of an electron beam from the surface of a nickel crystal. So, but their aim was to study the possibilities of electron diffraction, right. But once they observed a diffraction pattern, they confirmed the wave property of the electron as postulated by the even much earlier by de Broglie. So, what is the significance of this? Because at that point of time, when Davison and Germer were doing the experiment on the scattering of electron beam, the scientific world was not at all having a conclusive proof, experimental proof to prove the wave particle duality of the electrons. So, the wave particle duality of the electrons was actually first demonstrated by this electron diffraction experiment, and later as I remember it, Davison was awarded the Nobel Prize for his after 10 years or so on this technique, on this scattering technique. So, the diffraction of electron diffraction and the discovery of electron diffraction led to prove a very fundamental concept in science, that is the wave particle duality. So, in the science we never know where we end up while you will be exploring something else. You may be striking against something really fundamental, which can be really useful for many generations to come. So, that concludes my talk on the electron diffraction. So, for all these techniques like XRD, electron diffraction, neutron diffraction, you are having library of material available, where if you do an experiment on this kind of diffraction techniques, you will be always be able to compare your result with the literature. For example, XRD, which is having a whole lot of spectrums available in the literature, there is something called the JCPDS, right, which is a powder diffraction compilation of the powder diffraction files. It has more than 3 lakh or much more than kind of diffraction patterns, and then there are softwares available with the help of which you can always compare the XRD spectrum which you got with the XRD spectrum which was discovered much earlier, and you will be able to find out very easily the H-scale values or the Miller indices of your of the sample of your interest. So, the similar techniques do exist in the case of similar libraries do exist in the case of neutron diffraction also. So, with this this episode we conclude a whole lot of discussion on starting with the crystal structure, Miller indices, reciprocal lattices, the Brillouin zone, and then we were seeing how the what are the techniques, the diffraction techniques to study the crystal structure and whole lot. And now we are in the launching pad to explore different properties of these crystals when the electromagnetic or the sound radiations interact with these crystals, because we have put a perfect platform to concerning the crystalline structure or the Brillouin zone with these discussions. Hope these in the future discussions will also be useful to you. I encourage you to go into the different literatures available concerning the crystal structure before our next sessions on the topics like phonons, electronic band gap, energy band gap, and similar topics like the spectroscopy and all that. And thanks again for your attention, and see you next time.